Okay, today we're going to talk about the equation of a vector line. Okay, so let us draw a line first. Okay, so let's say we're talking about this vector line, right? So in general, what do we need to be able to write down the equation of this vector line? Okay, so first of all, we need a point, right? A point that is on the line. Okay, and secondly, we need a direction vector. Okay, so what is this direction vector, right? It's basically a vector that is parallel to the line, right? So we need a vector that is parallel to the line. Okay, so for instance, right, let me assign a point. Okay, so let's say this is point A that is on the line. Okay, and point A has coordinates 1, 2, 3. Okay, and then I'm going to assign a direction vector, right? So let's say, all right, so you can see this blue vector, right? So let it be the direction vector. Okay, let's say it's 4, 5, 6. All right. Okay, then our equation of the line would be 1, 2, 3 plus lambda 4, 5, 6, right? So lambda is basically a parameter, right? So it can be any real values. Okay, so lambda is an element of a real number. Okay, so what role does lambda play, right, in the equation? Okay, so for instance, right, I can say that if lambda is equals to 0, then it gives us the point 1, 2, 3, right, which is point A. If lambda is equals to 1, then it gives us 1 plus 4 times 1, 2 plus 5 times 1, and 3 plus 6 times 1, right? And that should be 5, 7, 9, right? So it gives us the point 5, 7, 9, which is somewhere on the line, right? So I'm not sure where it is, but it's going to be somewhere, right? So let's say it's here. There. So it will definitely be on the line. All right. So in general, there are infinitely many values of lambda. Okay, so you can imagine that each value of lambda is going to give you, a different point on the line, right? So all these infinitely many points will actually make up the entire line, right? So that's how the lambda works. Okay, now the equation I just wrote here is also called the vector equation. Okay, so this is basically called the vector equation. Okay, so you might be wondering, okay, so if the direction vector is just a vector that is parallel to the line, what if I choose something else? Okay, let's say I were to choose this as the direction vector. Okay, so let's say this pink vector, right, it has the same magnitude as the blue vector, but is opposite in direction, right? So that would mean that this direction vector would be -4, -5, and -6, right? Would that do? Yeah, actually that works also, right? So I could also do it this way, right? So I can say that the equation of the line is 1, 2, 3 plus lambda -4, -5, -6, right? So this is perfectly fine as well, right? Both of them, although they look a little bit different, but they're actually both correct. Okay. So you might also ask, okay, so you said that well, this should be a point, right? We need a point on the line and the direction vector. So earlier I used point A, right, as one of the point, 1, 2, 3. What if I were to use 5, 7, 9, right? Is it okay? Right, it's perfectly okay, right? So this is the line, and instead of using 1, 2, 3, I could have used 5, 7, 9. Okay. And for the direction vector, I could use either 4, 5, 6 or -4, -5, -6. It doesn't matter. Right? At the end of the day, it's going to give you the same answer. Okay, so this is also fine. Okay, so as you can see, right, when we talk about equations of a vector line, there is no unique equation to the same line, right? So each of these three, they are different, right? Even if it's a little bit different, right? But they're different. And they are all the equation of the same line. Okay, so that's something to take note of. Okay, so are there other forms to express the equation of a vector line? Okay, so yes, they are. Right, so what you just see here is basically the vector equation, right? We call it vector equation. So there's another form called the Cartesian, right? The Cartesian form, right? So it's good to know how to transition from the Cartesian to the vector form, right? Or from the vector form to the Cartesian form. Okay, so let's talk about some examples and how we can do the transition. Okay. Okay, so for example one, right? I'm going to use the same equation that we used earlier. Okay, so with the point 1, 2, 3 and 4, 5, 6. All right. Okay, so this is the vector form. Okay, so this is called the vector form. Now, how do we express this as the Cartesian form? Okay, now you realize that I can actually write this as a point, right? 1, 2, 3 plus 4 lambda plus 5 lambda plus 6 lambda, right? So as I mentioned earlier, right? So treat the vector equation like infinitely many points, right? They are determined, right? They are determined by lambda, right? So it will give us different points on the line. Okay, so R, what does R stand for? Okay, so this is actually the x coordinate, y coordinate, and the z coordinate of the point, right? So we're talking about 3D vectors here. Okay, so in other words, this is x, y, z. So this R actually represents x, y, z, right? The coordinates of x, y, and z. Okay, so there we have it. So x is equals to 1 plus 4 lambda, right? And y is equals to 2 plus 5 lambda. And z is 3 plus 6 lambda. Okay, so I'm going to make lambda the subject, right? So lambda is basically x minus 1 over 4. And in this case, lambda is y minus 2 over 5, okay? And this one is z minus 3 over 6. Okay, so since all of this, they are lambda, right? So I can say that x minus 1 over 4 is equals to y minus 2 over 5, and that is also equal to z minus 3 over 6. Okay, so in general, that is how we transform the vector form into the Cartesian form. Right? Okay, so let's look at another example. Okay, so let's say we have a new equation, right? So this is the equation of the vector line. Okay, so how do we change it into the Cartesian form? Okay, so I'm going to just express it as x, y, z. Okay, and that is equals to 1 plus 2 lambda, negative 1 plus lambda, and this is 2. Okay, so you can see that the z coordinate is independent of lambda, right? Because this one happens to be 0. Okay, so x is 1 plus 2 lambda, y is negative 1 plus lambda, and z is just equals to 2. Okay, so let's try to make lambda the subject again. Okay, so lambda is equals to x minus 1 over 2. For this one, lambda is equals to y plus 1, right? And for this one, well, z is just equals to 2. There's nothing much to talk about, okay? So for this case, right, you realize that the last coordinate, right, is independent of lambda, right? So how am I going to write the equation? Okay, so this is how we write it. Okay, so x minus 1 over 2 is equals to y plus 1, right? Because both of them are equals to lambda. And as for z equals to 2, I will just put a comma and then z equals to 2, right? So that will tell us that, this z coordinate is independent of lambda. All right. Okay, so let's look at another example. Okay, and we're going to talk about how to transform the Cartesian form back to the vector form. Okay, so I'll just write it here. Okay, so let's say we are given this particular equation that is in Cartesian form, right? So x minus 1 over 3 equals to y minus 3 over negative 2 equals to 4 minus z, right, for instance. Okay, so, well, I know that all of this they are equals to lambda, right? You realize that there's no comma here, right? So each of them is equals to lambda. So x minus 1 over 3 equals to lambda, right? And y minus 3 over negative 2 is equals to lambda. Okay, and 4 minus z is equals to lambda. Okay, so what I'm going to do here is I'm going to make x, y, and z the subject. Okay, so x is equals to 3 lambda plus 1. Okay, and y would be equals to negative 2 lambda plus 3. Okay, and z would be equals to, well, 4 minus lambda. Okay, okay, I can also say it's negative lambda plus 4 if you want. Okay, so why am I writing it like that? Okay, because I'm going to split it up. So x, y, z is equal to, okay, so you realize that the points here, I mean the numbers here, 1, 3, and 4, right, they actually belong to a point on the line. Okay, so I'm going to write that first, right? So that's 1, 3, 4. Plus, I'm going to factorize out lambda for this, right? So this is lambda, this is 3, negative 2, negative 1. Okay, so you can see, right? So this is the equation of the vector line in a vector form now. Okay, so let's look at one last example. Okay, so again, we have a Cartesian form. Okay, so y minus 4 over 2. Okay, so you realize that there's a comma here, right? Instead of equal all the way. All right, so that tells us that this x coordinate is independent of lambda. All right, so I just write it down. Independent of lambda. Okay. Anyway, if you prefer mu, you can use mu or other kind of parameter, right? But I just prefer to use lambda. Okay, so it's okay. So just write x equals to 3. Y minus 4 over 2 equals to lambda. And z plus 3 over 5 equals to lambda. Okay. So this one I will not touch because x is just equals to 3, right? But for this two, I can make y and z the subject. Right, so y is equals to 4 plus 2 lambda. Okay, so z is equals to negative 3 plus 5 lambda. Right. Okay, so our equation would be x, y, z equals to, this is 3, 4, negative 3. Right, plus lambda. Okay, so take note that the x coordinate, which is independent of lambda, I'm going to assign a 0 here, right? So that means it will be independent of lambda, right? 0 times lambda is just 0. And this one will be 2, this one will be 5. Okay, so our equation in vector form would be this. Okay, so yep, that's the end of the video. Thank you.